This is an exercise of conceptually understanding how Coulomb's force changes if either of the charges or both of the charges change in their magnitude, double, half, quadruple, become 3 times less or something like that, and or the distance between the charges changes. So in the first, what we're going to work with, we have the original configuration of the charges. I have a positive and a negative charge, and they are 10 paces, if you will, 10 boxes apart from each other. Because they're opposite in charge, they're going to attract each other with equal and opposite forces. You can think about it in terms of Newton's third law, always works here, and also in terms of finding Coulomb's force with the same equation for both of them, which is force electric equals absolute value Q1, Q2 over distance. Then in A, all of a sudden I have both of them negative, but that only changes the direction of the force. However, not only is one of them negative instead of positive, now if you look at the distance, it is half of what it was before. So I'm going to say RA is R over 2. I'm going to work with my original formula. The distance now changed. Distance should still be squared, so nothing changes in that department. So R, and now it is halved, so it's R over 2. If you have a square on the 2, that becomes a 4. And since the 4 is in the denominator of the denominator, it comes upstairs as a 4. And what we end up with is 4 times the original electric force. So the original electric force was just the 2 charges over the distance squared. Now it's half of the distance, and therefore the force itself is 4 times greater. So I'm going to take and instead of 2 boxes, get that 4 times the 2 boxes. So they are repelling each other, and the force is now 4 times stronger than the original force. And what I did is I worked with the original formula and replaced something that needed replacing. Case B. Case B, compared to the original, again, I am going off of this original situation where I had 2 charges, a distance r between them. Now it's the same distance, but now one of the charges is doubled. So again, I'm going to grab my original formula, and the only thing that changed for me here is one of the charges became doubles. All right, and everything else is the same. So if everything else is the same, that tells me that my force now doubled of the original. When the distance remained the same, but one of the charges became double of what it was before, my force doubles. Now, my new distance is double of what it was before, and one of the charges is 4 times. This is getting serious. So not only did they change a charge, they also changed the distance. Grab your original formula and work with it. So we have to make one of the charges 4 times of what it was before, and the distance doubled. So it's going to be the square of 2r. Be very careful here. 2 is also squared. So because 2 is also squared, you're looking at 4 over 4. So 4 came from the fact that one of the charges is now 4 times what it was before. And 4 came from the double the distance. Everything else is the same. Still Q1, Q2, absolute value over r squared, which tells us that 4 over 4 cancels. The force is the same of what it was before. And the very last one, we have everything changed now. One of the charges is 1/4 of what it was before. The other one is double of what it was before. And then finally, the distance is again half. My original formula looks like so. 1/4 and 2, Q1 and Q2. And the distance halved, and I have to square. Remember, I have to square that 1/2. So then I have 1/4 here, 1/4 here, and 1/4 here after squaring. That leaves just this double, which means that after the last configuration change, I end up with double the original force Fe. Practice just manipulating the formula without any numbers to conceptually understand what happens with the electric force when charges or distances change.